Our next speaker, Aleks Owczarek, who was one of Rodney's students, he'll talk on exact solution of asymmetric gelation between three walks on the square lattice. Thanks, Aleks.
Thanks very much, Murray. Good morning, good evening, wherever you are. Of course, it's a sad privilege to speak at this meeting, and I will talk about particular problems that may be a little bit adjunct to some of the other work that have been presented. But I do want to highlight a couple of things in terms of general principles of working on exact solutions and problems in mathematical physics that I learned in my time as a student with Rodney. I suppose one of those things is working on the right problem. I recall that when I first started, Rodney suggested some different problems, and one of those was to do some numerical work on I think they were corner transfer matrices of a particular problem. And the idea was to see if the pattern sort of behavior of the structure of the corner transfer matrices were similar to a previous problem which led to exact solution. I didn't find that, so that's why it never really went anywhere. But it was the principle of firstly doing some numerical work to find out, is the problem that you're working on the right problem, which is something that I wanted to highlight today. And also that you need to sometimes do a bit of work to find that right problem, and a bit of perseverance, which I think is another thing that I learned from Rodney, was evidence that sometimes you have to wait a while and work diligently to find the right to find a solution. And this is apropos of this talk today, because I spoke about something similar 10 years ago at the Baxter meeting in 2015, and this is sort of the next chapter of it, which has taken this long really to find. Okay, so what am I talking about? The general area is about the solution of interacting directed walk models of polymers in solution, and these models occur in combinatorics as well as statistical physics and in probability theory. And there's a way of looking at the exact solution of single and multiple directed walkers, and the focus from a combinatorial point of view is to work out the exact generating function for fixed numbers of walks, not infinite number, a fixed number with certain sets of interactions. And over the years, we've looked at, myself and collaborators have looked at various different problems where we've tried to make the problem more complicated to see if we can still solve it and get some interesting physics out, as well as getting some interesting mathematics out. The way you go about solving these problems is you find usually a recurrence equation for the partition function, or in fact a functional equation, which is the sort of more modern way of doing for the generating function. And the solution of these problems can be various different formats. They can be you can have a rational generating function, an algebraic generating function. You can have a differentially finite generating function, or you can have non-definite solutions like Q series for these generating functions. We found all different types. It does relate to problems that you may be more familiar with in traditional lattice models, such as the 6-vertex model, and the various. I'm going to tell you about 3 different sort of underlying models, and one of them is so-called vicious walkers, which is previously studied. That's not the focus of today's talk, but that's related to free fermions. And there's actually a deep connection between a theorem in probability theory and combinatorics called the Lindstrom-Gesell-Viennow lemma, and the Batter-Ansatz. And multiple walkers in this lemma gives you a determinant of partition functions when you of single walkers, and that arises effectively because of the lemma, but it's clearly related to the Batter-Ansatz. But an interesting thing to point out is that when you look at these problems, your generating function always is d-finite, and we have found non-d-finite solutions. So some of the technique for solving these problems can go beyond what you can find in that one. Okay, so we apply a basic model, a type of multiple directed walkers, and we add in different types of interaction, and these can give non-finite, non-definite solutions. So the vicious walkers, which goes back to well, a long way, but there's a famous paper by Michael Fisher in 1984, which talked about vicious walkers. And there you don't have any interactions. The walks don't touch each other. They're vicious, and so it's a little bit. You can put some kind of interactions, but on them, but that's usually not the case. But the two types I want to talk about today, osculating and friendly. Osculating walks are ones where you can share the walks can share sites. The different multiple walkers can share sites, but not lattice bonds. And friendly walkers, which is what I talked about in 2015, you can share sites and bonds. So here's a plotted history of some of the work that's been done previously, where there's many vicious directed walkers. As I said, goes back to Michael Fisher, the Lindstrom-Gesell-Viennot theorem, which is around the same time in 85, and various other works. Friendly walkers and oscillating walkers a bit later. Richard Brack has looked at oscillating walkers for some time, and so did Mireille Bousquet-Malouf from University of Bordeaux, and we'll be mentioning some of her work again. So with a wall and no interaction, there's a LGV problem. Many vicious walkers, Krutenthaler, Goodman, and Viennot in 2000. And if you take a single walker and you have various interactions, then you can extrapolate to two walkers with wall interactions and many vicious walkers. Okay, but where we sort of then moved to in the early 2010s was to look at friendly walkers with various different types of interactions, and I'll tell you momentarily how we've looked at those problems and how we solved them. So my collaborators, Andrew Recknitzer from the University of British Columbia, and various students of ours looked at two friendly walkers interacting with a wall, two friendly walkers with two types of interaction, interwalk interactions and wall interactions. And then what I talked about in 2015 was three friendly walkers with symmetric interwalk interactions, and that appeared the next year. And what I'm sort of talking about today is, well, we tried to generalize that in various different ways, and this is one way we tried to generalize it, and it's taken us 10 years to get anywhere, really. So what was the way we solved those three different types of problems of friendly walkers was to use the so-called kernel method, in fact, the Obstin kernel method, which is creation of various people, but Mireille Bousquet-Malouf was a leading light in that. But it got the actual original kernel method goes back to Donald Knuth in 1968. Very, very simple idea, appears in his book, one of his books. And you start off with a combinatorial decomposition of your set of walks that leads to a functional equation. And then something that I also learned from Rodney was that sometimes the variables that you have are too restrictive. Sometimes you need to add extra variables or generalize your problem to actually solve it. Those extra variables are helpful, and it occurs here as it occurs in various problems in lattice statistical mechanics you add these extra so-called catalytic variables, and those extra variables allow you to solve the problem. The generating function you want is the values of those catalytic variables at so-called boundary values. Your functional equation is written as a bulk equal boundary terms, and the bulk term has this simple rational function in it called the kernel, you set the value of what you try to do is you set the value of the catalytic variables to make the kernel vanish, and so you just get a solution for the boundary term. It's sometimes easier said than done. So, and the reason for that is that you have, in the problems that we look at, you have to add in several catalytic variables. So it's sort of like complex analysis in several variables, not as easy the case. And that gives you this obstinate kernel method. So it goes back to Mireille, Buskin, and Liu, and there's a paper in 2010 with Marnie Mishner and Mireille, which is a nice summary of that work. The solutions are not always definable, so it does go beyond that things that you can solve with that LGV, Lindstrom-Kessel theorem. It's related to various things that you may have heard of, mentioned diagonals of multivariable rational functions. There's a connection here and a connection to some work in probability theory, which has been ongoing for many years, and also provides some different types of exact solution, so-called quarter plane and other segments of the plane, random walk problems in 2 and 3 dimensions. And they're a live body of work and connected to this obstinate kernel method. So what was the problem that we looked at that I talked about in 2015, which was 3 friendly walkers in this so-called watermelon configuration, where the walks start in one point and end up back together again, and in between they can share edges and share sites. And we actually talked about a slightly more general problem where you had 2 interactions, but for today's talk, it's not really relevant. So I'm just simplifying it to the 1 interaction, where we counted, where you can count the number of shared sites between any 2 walkers. So to make that clear, when you have a triple sort of coalescence of the 3 walkers, that gives you 2 double contacts, so contact between the middle walker and the bottom walker and the middle walker and the top walker. So this configuration has a Boltzmann weight of C to the 11, where C is the Boltzmann weight for just a single contact between 2 walks. So this is another way of writing it down. Double visits gives you a fugacity C. The triple visits gives you C squared. The walks start and end together. MC is the number of double contacts, and your partition function is what you might expect, summing over all configurations, C to the M. And the generating function, which is what we found last in that 2016 paper, is this simple generating function. And so I said the way to solve this is to add these catalytic variables in. What are the catalytic variables? Well, the walks start and end together, but of course, intermediate, they have any distance between the top walk and the middle walk and the middle walk and the bottom walk. And you have to add in variables which count the half distance because the measure we put on, between the final vertices of the top and the middle to the bottom loops as you move through the configuration. So you actually try to find this generating function f of R and S, C, Z, and you find a functional equation for that. Well, you can do that, and I'm going to tell you how to do it. That was last time. You can find this functional equation, which you find from the decomposition of the walks. It's made up on one side of a bulk term, which is a kernel. It's a rational function, 1 minus Z, R plus 1, S plus 1, R plus S on RS. multiplied by the general generating function in R and S. And then you have a series of so-called boundary terms where you specify one of the variables to be 0 or both variables to be 0. And in fact, setting both variables to 0 gives you watermelons. Now, the trick here is that you've got one equation. How do you find the solution? And I said it's about putting in particular values of R and S. Well, the kernel is symmetric under a set of two transformations, which are both involutions. You can swap R and S, and you can make S go to R and S, and that actually forms a group. It's a group of 12 symmetries, and that gives you actually 12 equations. So you actually have a lot more equations. Okay. And we solve those equations, and you get this solution for the generating function. So again, I'm not going to explain how you actually did it, how we did it. But the important bit here is that the actual solution contains this function j, and j is a d-finite function, but not a very nice d-finite function. So you can actually find a differential equation for this. It's, I think, of order 26, the solution to this for this function. So it's a d-finite solution, and one which is not the simplest. But we could analyze the physics of the situation by going back to the differential equation and finding the critical exponents in that way. And again, I'm not going to go into that too. So what we wanted to do afterwards was, how about we generalize this in various ways? Well, we could try to find a model where we add interactions, a different interaction between the top two walks and a different interaction between the bottom two walks. Okay, and we tried to do that. We tried multiple times. We thought we had various different ideas, but the problem is that breaks one of those symmetries, the S to R. And while you have different equations, you don't seem to have enough equations to solve the problem with the obstinate kernel method. So we thought, well, after quite a long time of just trying and not working with, well, maybe we're not working on the right problem, okay? Because we already know that this symmetric solution is d-finite. I've just shown you this symmetric solution, and it's a very high order DE. So if it was asymmetric, you'd think it would be horribly high different order differential equation, and guessing maybe rather difficult. And the solution will require something special. So we thought, well, we'll just go back to the oscillating problems and look at both stars and watermelons. So stars are basically you sum over all the endpoints. Instead of fixing the endpoint of the walks to end at the same place or similar, you sum over all possible endpoints. Why that might make it simpler or not, is pure speculation. But in fact, so let me just explain what the problem we did look at eventually is these are oscillating stars. So oscillating walks can't all be together at the one point if you have three of them, because then you'd have to share a bond of the lattice. So we start them one lattice spacing apart, and moving in this direction. They can end anywhere, and we sum over all endpoints. So this configuration has a Boltzmann weight of A cubed B squared, where A is a Boltzmann fugacity associated with the coalescence of the top two walks, 1, 2, 3, and B is related to the touching the oscillations of the bottom two walks. And it's a partition function in A and B, and the generating function, which I'm going to label 3 from the reason which will become clear in a moment. And we found G3. So how do we do that? Well, I did find some exponents, and so I don't have time. I'll just do the normal definitions. The free energy kappa in appropriate units is related to the log of singularity of the generating function closest to the origin. So that's the sort of relationship between the free energy and the behavior singular behavior of the generating function, and the growth, which is this is a normal kind of equation for the scaling behavior of the partition function, which goes as mu to the n to an exponent, called the entropic exponent, gamma minus 1. And this mu is also related to the closest singularity of the origin of the generating function. It's related to kappa, the free energy. These things are all effectively the same thing. And to get an idea of what the phases are, I define these two order parameters, A and B, which are the thermodynamic limits of the average number of contacts between the top two walkers divided by n, and the thermodynamic amount of contacts between the bottom two walkers in B. Okay, so you could imagine you could have different phases where these A and B are 0, or one of them is 0 and the other one's not 0. And they would relate to situations where if they're both 0, the three walkers just wander off and don't have that many contacts. They might start off having some contacts and then they wander off generically, thermodynamically. Or one of them, B, is 0. So the bottom walk wanders off, but the top two walkers stay close together. That's when calligraphic A is bigger than 0, that B is equal to 0. The opposite situation where the bottom two walkers are zipped together, but the top two are not, or all three walkers are zipped together. And these are, you can imagine, are all three different thermodynamic phases. There's 4 possible phases. And the exponents, which are related to the phase transitions, a normal exponent alpha, which is related to how the free energy behaves as you cross the boundary. T is just generically the distance in whatever units you like. And kappa goes as T to the 2 minus alpha. The order parameters will related to this behavior at the phase transition point will go as 1 minus alpha. And there's another important exponent, but they're related, called the crossover exponent, which relates to the behavior around the phase transition, called phi. But you can calculate it by looking at the number of contacts right at the transition, which goes as n to the phi. And in fact, many years ago, we found that phi in these problems that we'll look at, generically phi is 2 minus alpha, so that they're not independent. Okay, so we went about finding a functional equation for this problem. Here it is, different kernel, here is the functional equation. It sort of looks similar, different, and I'll highlight that there's a and B here, but you can see things would simplify if A does equal to B. And what we want is when R and S is at 1, not R and S 0, because we want to sum over all possible endpoints. So we want this function f11 a, b, z. But we're still not clear to us we had same number or enough equations, so which was disappointing. But we thought that we were in with the chance of solving this problem. Why? Why did we think that? Well, thing is that firstly, let's go back to just 2 walkers. If you look at 2 walkers, which for oscillating stars, then the generating function is a simple quadratic algebraic equation. And you can get all the information out you want. You can find the asymptotic behavior of the average number of contacts simply and the associated order parameter, and it has 2 phases depending on whether M, in this case, which is the average number of contacts between the 2 walkers, is 0 thermodynamically or some value, which you can calculate. And this goes back to work by Michael Fisher, but also Pretori and Inyer in 2001 and Goodman and Vogue in 2002. So they all contributed to this solution. Okay, so with 2 walkers, yeah, but you've got 3 walkers. Why would you expect that to be simpler? And you can work out what the exponents are. It's a continuous phase transition where alpha is 0 and phi is a half, and you know what the phase transition is. It occurs at A equals 4. Well, you can solve 3 oscillating stars as well. And that is also an algebraic function. It's also quadratic. So it's not that horrible d-finite solution of Fogle. It's a beautiful thing in one way, depending on your point of view. But this is clearly a lot simpler function. So we think, well, we thought morally that, in some mathematical moral sense, that if we generalize this problem, it should be a little bit nicer than trying to generalize something which is already quite difficult. And once again, you can find all the exponents and phase behavior of this problem. Again, it has 2 phases, depending on n is 0 or not. And you can get everything out that you want. So again, the transition is continuous, which is very nice. And you can work out what these entropic exponents are. It's -1/2, the free phase, and 1 other ones. So you can get all the information you want if it's symmetric. So how do we solve, in inverted commas, the problem when A equals B? Because we said, well, we can't really, we're having difficulty with the obstinate kernel method. So this is the only kind of new part, in one sense, of this talk, is what we did was, well, we looked at different integer values of A and B. A equals 1, B equals 2, A equals 2, B equals 3. And we generated very long series. And then you can get very long series because you've got the functional equation, not because you're doing some numerical work, you're actually looking at configurations, but because you've got you've got the functional equation, you can generate very long series. And there's this lovely package in the Sage computer system, which allows you to guess solutions if you have a very long series. And you can find that for each of A and B, you get a quartic. And in fact, by sufficient A, if you choose sufficient integer A and B, you can guess the actual quartic equation which your general A and B, without being integers, satisfies. And then you can, of course, show that it satisfies the functional equation and show that you have the right equation. So we found the quartic equation, and because you can solve a quartic, we could write down a solution. We haven't done that because the actual quartic equation takes 2 pages of A4 in 11 point. And so it's not something nice to write down, but you can write it down. And once you have the quartic equation, you can find D, of course, as well. You can find the important aspects of that quartic equation, and the most important coefficient in the quartic equation is the coefficient of g to the 4. And that allows you to find all the exponents and stuff. So we could find that there were 4 singularities to the problem. Those 4 singularities related to the 4 different phases. We could find a phase diagram where you have these free bottom zipped, top zipped, and fully zipped phases. And we could find all the exponents that you'd ever want, which I'll just go through quickly because probably maybe not a problem you're interested in, but we an explicit solution for everything. So we got an explicit solution for everything without actually using the kernel method, but working on a nice problem. And you can find, we found some new exponents, some quarters rather than halves, which expands the world of these kinds of problems. But it all comes back to the sort of things that I learned, some of the things that I learned from Rodney about tackling the right problem, and then looking for the way which gets you that solution. So let me conclude with saying we looked at this model of asymmetric gelation of 3 oscillating walks on the square lattice. We found an algebraic solution, a particular quartic. We focused on oscillating stars because the friendly watermelons proved just too difficult to analyze. And we found a solution in a cunningly different way, or just because we were desperate to use, but a very nice way, this Sage package at a fixed number of integer values. And we're currently writing up some work on 4 walkers, but the 3 walker asymmetric solution you can find on the archive, hopefully in your journal sometime soon. So thanks for listening. And again, it's been a real pleasure to give this talk here. So thank you.
Good, thanks, Alex. Do we have any questions online or in person here? Jean-Marie?
You mentioned diagonal and fractional functions. Yeah, it's possible that in all these cases where we have power series, of course, with a finite radius of convergence, when it's in definite case, there is this Christoph's conjecture which says that we are automatically diagonal of rational functions. This conjecture is a bloody conjecture. Still, after 30 years, one doesn't know if it's true or not, or it remains a conjecture. So it could be that all the time we have definite, we have diagonal of rational functions.
Yeah. Yeah, I know that. Yeah, that's something that's still of interest, and yeah, a nutty problem. Thanks, Jean-Marie.
Okay, let's thank Alex again.